what we did yesterday, we introduced some of the specific tools that people get to use a lot in practice. Comes down to the measures of dislocation. One of those, two of those tools that we introduced to class was the sample mean and sample median. Both of these tools serve basically the same function. Let us know where the center value of certain distribution is, but in detail, how these two different tools work in practice is quite different. Sample mean is defined as the sum of all those elements, observations, and divide the sum by the size of sample. And then median is literally the value observed in the middle of the distribution when you rank them in terms of its size. Both are used a lot, but the slight difference between this first tool, sample mean, and then the second one is sample median. The second guy is a lot more robust to potential outliers. And this was well illustrated by the example that we went through last time. So we first handled these 8 different numbers in one random sample, and then purposely dropped this 11 and then replaced by even bigger outlier, which is 71. In the case of sample mean, from switching from the correct sample of the first to the wrong sample of the second, there's a sudden, quite large, significant increase in the computed sample mean of 22%. But if you switch with the exact same 2 sets of random samples and then use the sample median instead, there's still some rise, but the magnitude of that increase is a lot less in the case of median, which was just about 5%, 5.2%, which refers to us that the fact that this median is a lot strong or robust to potential outliers, a lot less affected by them, because you only care about those observations placed in the middle of the distribution. Don't even take a look at what's far out to the left, and what are those entries, numbers far out to the right. So they don't even come into the picture when you get to compute the median. So that's why it's a lot less affected by those outliers. And then we move on and introduce, again, the 2 different measures of variability, or simply spread. And one of them was a range, and the other was a sample variance. So the first one is rarely used in practice because it's way too simple and naive. So range is just a simple difference between the max value in the sample and then the minimum value. Only depends on the 2 extreme values. So it doesn't even consider what's inside, what's in between. So again, just like the case of sample mean, this one is even more vulnerable to potential outliers, because if all other observations are packed around the mean, but then you have a huge outliers on each end, but that's obviously not good representation. You just simply take the difference between the mean and max and claim that that's how much spread that we are having. Because if you simply drop those 2, measure of the spread will hugely decrease. So that's not a good representation. Better representation of the actual amount of spread given in the distribution is the sample variance. Mathematical definition was given by this one. First, compute the sample mean of those sample points. Subtract them from each one of these observed values, x1 through xn. Don't forget to square them, because if you simply sum these deviations, you end up with 0, for the reason that we saw yesterday. So if you sum up these squared values and then divide the whole sum by the sample size minus 1. If the sample size gets large, say 3,000, or even bigger than the 10,000, doesn't matter really much whether you subtract 1 or not, because still both are big numbers. But if the sample size is down to say 20, it actually makes some difference whether you divide the whole thing by 30 or 29 or 19 or 20. Otherwise, in practice, a lot of people confuse these 2 and then just use both of them. So unless it's specify those questions, use the unbiased version, or the one that divide everything by n. Otherwise, note it, you just allowed to use both of them, either one. But if I say that please use this, if the question specify what the choice should be, then of course you have to use that one, specify the question. Otherwise, you get some penalty for that. And then once we have this, the measure of the variation or spread in the distribution, we can simply take the square root of it so that we can obtain so-called sample standard deviation, which is defined as this square root of the sample variance that we just computed up there. And then we went on to think about these important properties. Since we did it yesterday, I'm gonna skip it. And I ended up with this the convenient formula. Instead of just using the definition of the sample variance, we can just break it into two parts. First, the sum of those squared x's, sample size times the square of the sample mean, and then divide this difference by either n or n minus 1. That will basically give us the desired sample variance. It's just a computationally more convenient and easier to work with, but you still get the same answer, exact the same answer, whether we use this formula or just use the definition. That's where we stopped. Just a recap. Comments? No comments. Okay. Two more useful facts. We prove them and then we get it over with it. End of the first lecture note. And then we move over to the second one, which is about probability. Lecture note number 3 and 4 were posted on the website this morning. And I sent you guys the email. So if you haven't checked it yet, please do so, because we're gonna need both of them next week. Lecture note number 3 is simply about the combinatorics. The combination, permutation, maybe combination of both. So we're gonna spend about half a lecture, maybe 3/4, but not even the entire lecture. But then what's coming up after that, lecture note 4 is a major one, conditional probability. So if I have to choose one single topic, that's the most important as far as the midterm exam is concerned, that's number 4. Conditional probability, that's a major one. So make sure that you have access to both of those notes for lectures next week. As far as today's lecture is concerned, we just finish up the first one, this one, 3 more pages, and then we move over to the second lecture, which is about probability. But then probability lecture is a minor one. We can finish up today. So we are ready to move over starting Monday. Okay. So the first proposition that we need to prove before we leave this one is following. Assume that there is a random sample of x1 through xn. So that's just a random sample. N different numbers in our sample. And then you do transformation of these by simply adding some fixed constant c. We don't know what the number is. We just know that that's just some fixed number. Could be positive or maybe negative, but some fixed number like maybe 10 or -5. But the important thing is that you have to add this same fixed number to each one of these observations in your sample set. So first, new sample point y1 is defined as the sum of that original x1 plus c. Similarly defined the second transformed sample point, which is y2, defined as the sum of the second x this time, and then still same c, and so forth, until you come up with this last y, which is defined as the sum of this last x and the same c. You see that once you do this transformation, you come up with a completely different new set of sample points, y1 through yn. So since it's a different sample, there must be different sample variance and sample standard deviation. And then the first proposition states that whether it's a sample sample x or sample y, if you compute the sample variance correctly, those two things are exactly the same. How do you show this? Intuitively, this one should be obvious. The reason why it's obvious because original distribution of those sample points axis right here, say. If you simply add the fixed number c to all those observations, so that's the distribution of x. What happens to this curve? What's the distribution of y if you just simply add the fixed c to all those axes? So original axes are here. That's the shape of that distribution. Imagine that there's a histogram. But then if you add those fixed little c, you see that this little c there, So same number gets added to each one of these x's, and if you plot that histogram for that transformed x, which is y, what is the shape gonna be? Anyone? Say the C is 3. If you add number 3 to each one of those x's, what happens? Well, you basically slide it through the right hand side as much as 3. So if the mean was here, the mean for this one is just a 3 bigger, so distance between this mean and that mean is going to be 3. You just slide it to the right hand side. If C is negative number, you slide it to the left. That's it. So there's no change in the shape. So amount of spread, variation for the first distribution should be exactly the same as that in for this yellow, because you basically slide it. Don't distort the shape. Shape itself is exactly the same, stays intact. Doesn't change at all, it's just the location changes. So it's obvious. If you compute the sample variance for this y1, should be exactly the same as that for this yellow, because there's no change in the shape of this curve. It's just a different location, whether it's more to the right or whether it's more to the left. But shape-wise, it's just the same as before. So the answer is somewhat obvious. Since the sample variance represent what's the amount of spread in certain distribution, since we didn't change the shape of that curve, that quantity for y should be exactly the same as that for x. But that's just our hunch, our intuition. You cannot draw the picture on the exam and then claim that that's the case. On the exam, if you are asked this one, you actually have to go through those step-by-step analytical solutions, mathematical solutions. So how do you do it? It's a simple. Usually you are asked to prove A is equal to B. So the trick is, should be one of the following. Starting from A, try to reach B. Or the other way around, start from the right hand side B and then try to show that that leads to A. Either is fine. But maybe in this case, moving from left to the right will be more straightforward because y is the newly defined one. So the suggested approach to handle questions like this one, you first define the left hand side, which is the sample variance for the new set of observations, bunch of y's. And that's nothing but this. Right? So that's the definition that we introduced before. You remember this definition? But that one was written in terms of x. Now you replace all these x's by y's. Then that's going to be the sample variance of those y's. Nothing really new. Okay? So the first equality is nothing but the definition of sample variance, whether it's for y or whether it's for x. So structure-wise, it just stays exactly the same as before. By the way, if you look at those lecture notes that have been posted so far and those lecture notes that will post in the future, some of those questions are not answered. So if you look at the note, just this, the proposition is stated, but the proof section is completely empty. I mean it. It's not a typo or mistake. It's like I was typing this and then doing something different in 5 minutes and I come back and forget to write the answer. No, I actually mean it. So how to fill in this blank? Come to class. I show you the solutions. It's not posted. So the first time I taught this class, I just posted everything, questions and answers, and one of the things that I realized as the class moved on, nobody started showing off. Especially after the midterm exam. I remember one occasion that I did a lecture with only one person. It's like a private lesson or something. I mean, the lower the enrollment, it's actually easier for the instructor because, handling 5 students is easier than handling 40. But you pay lots of money to attend this one, so you want to get the best out of it. And the way to get the best out of the school and instructor is just attend the lectures and come to office hours and everything. Not just going out and have some fun. Well, sometimes it's important, but not all the time. So some of those answers will not given, but I'll provide the answers during lectures. So make sure that you come to lectures. So the suggested solution is this one. So first write out the definition of this sy squared, which is this. And then the second step is gonna be, since you want to reach this one, you want to show that the sample variance for y same as that for x. You somehow have to connect these y's to x's, because that's eventually where you want to go. But then the relationship is the given by the question itself. yi is defined as the xi plus the same c, and then subtract the sample mean of y, which is the same as the sample mean of x plus c. So for this part, so just like what we did yesterday, you just manipulate those summations and show that those two sample means are related in a very straightforward way. So for this part, the reason why I know it that way is because sample mean of y defined as this, but then further we know that yi is written as xi plus c. So if you distribute this summation to each one of these terms inside, the first summation is going to be this, and the second sum c. But this fixed number c is free of this index I, so you can pull it outside. And if you pull it outside, you put c in front of it, and then what's remaining inside is just a 1. But you are just basically adding this fixed number 1 n different times, so that's nothing but n. So this n here and another n outside, which is inverse of that, so they kill each other. So you're only left with c. But then the definition, the stuff before this c is nothing but the sample mean of x, and you're only left with this c. So just replace this sample mean for y using this property by the sample mean for x plus c, but you have to subtract the whole sum. So you put the negative minus sign before each, here and there. So this c and that c, they kill each other because they're the same c's, but different signs in front of them. So you're only left with xi minus sample mean for x squared, and the stuff remaining is nothing but the definition of the sample variance for the first set of x's. So done. Quite easily. Okay. Anything that I can help? No. Forget it. Second is the solution. Second proposition. Now you come up with a constant multiple of those original x's. Instead of adding c, now you want to multiply those individual x by some constant fixed number c. So accordingly, first y is defined as the same c times the first x. Second y is defined as the same c times the second x, and so forth, all the way to the last y, which is the c multiple, constant multiple of this last x. If that's the case, instead of just simple addition, there will be some difference between the sample variance for y and sample variance for x. And difference is governed by this fixed number c squared. And then you have to multiply the original sample variance by that number. Then you get the sample variance for the second distribution. So how do you get this one? Same as before, start from the definition of this left-hand side and try to reach this right-hand side. So that's what should be done. So write out the definition of the left-hand side, which is the sample variance over y, which is the first one here. And then I'll simply replace this yi by its relationship to x, which is c times xi. That's the way we define it. Connection between y's and x's. It's a constant multiple of one should lead to the other. And then if you take the sample mean for those y's, and that's nothing but the constant c times the sample mean for x. And for this one, go back to the simple illustration, replace this addition by multiplication. So replace this x plus c by c times x, but then this part goes away. And then for the same reason, you can pull this c outside, so you have c there. But then if you put this using this big bracket, that's nothing but the sample mean for x. So you easily see that the sample mean for y is nothing but the same constant multiple of the original sample mean for x. So y bar can be replaced by c times x bar. Is it hard to see? If I put the light on, is it better for you to see? No problem? Don't care? Okay. So that's what it is. Once you figure out the relation between the sample variance and sample variance for y and that for x, it's easy to figure out that for those standard deviations. Take the square root of the left hand side, and that will give you the sample standard deviation for the second set y. But then you have to still take the square root of the stuff on the right. So the first term, what's going to happen is that you take the absolute value. You have to put the absolute value because if the c happens to be some negative number, sign might have to change. So in order to prevent that from happening, you just have to take the absolute value to make sure. Of course, if the c is positive, you don't have to, but just in case the c is some negative number, you better do it to make sure that the equality still holds. And then the square root of the x squared is nothing but sx. Right? End of it. One tiny numerical example. Don't ask me what Young's modulus is. I just stole it from someone else's lecture notes. If you take a course in physics, you know who Young is. He's a British physicist. I don't know what his modulus is. Just look it up. Google it or something. So there are 5 different numbers. From certain cast plates, he obtained these values of modulus, starting from 116.4 and all the way to this last observation, 115.8. You're asked to compute the sample mean and sample standard deviation, sample variance for these. Mean is just as simple as it is. Add them all up and divide it by its size, which is 5, and you get the 115.58. And then for sample variance, you are allowed to use either its definition or the useful formula that we derived yesterday by doing the decomposition stuff. But if you just stick with the original definition of it, just subtract this computed sample mean from each of these 5 modulus value. So subtract this the shaded one from the first entry, and the difference is going to be 0.82, and then you square it. Don't forget to square them, because if you just sum up those differences, you end up with 0. And then do the same thing for the second entry. Subtract the same sample mean from the second modulus value, and then difference is going to be 0.32. Square them, and then repeat it for the rest of the remaining 3 values. Sum them all up, and then divide it by degree of freedom. Don't forget to subtract 1 here. If you just leave it as it is, 5, that's the sample size. But if you subtract 1, that becomes the degree of freedom. And then the desired answer, if you compute everything correct, it's going to be 0.82, 482. Quite easily done. End of the first lecture note. Any comments? Pretty simple, huh? Okay, you're done with it. over to the second one, which is probability. There are 11 lecture notes in total for this class. And as we move along, the length and difficulty of lecture notes will get higher and higher. Getting longer and longer and getting more and more difficult. So by the time we get to the last lecture notes, 11, I think it's about 60 pages or something. So it's pretty exciting, huh? You prefer the other way around? Starting with a hard and long one first and then go down the road with a smaller and then short. No. So 11 lecture notes, and we are done with the first two. We will finish the second one today. Number 3 and number 4 are posted this morning on the web, so make sure that you download them. You don't have to print them out. You can just simply bring some blank sheets of papers or some notes, or you can bring your laptop if you want to. Whichever way you find most convenient and comfortable with, just do it. But the key thing is that you should know you should know how to have access to those, whether you download them or print them out. So number 3 and number 4 we will do next week. And number 4, like I said before, it's a major one for the midterm. So if you have some free time over the weekend, might be a better idea to go over them just briefly, not too much detail. Don't get into too much detail. And the remaining 7 notes will be updated as we move along in this class. So basically, per week, 1 lecture note for the remainder. Now those lecture notes are rather minor and short, so we cover 2 or maybe 1.5 per week. But as we move along, the length gets longer and longer, and difficulty gets higher and higher, so we have to obviously slow down. So what are some of those important agenda in this second one? Several definitions first, and then we do some graphical methods, things like a tree diagram or Venn diagram, and then we handle some of those examples, how to use them in practice, stuff like that. So first is first, some definitions. Random experiment. Definition: it's an experiment whose outcomes are known but cannot be predicted in advance. Examples: coin tossing. If the coin's fair, the fair means there are equal chances of having both the head and tail. So 50-50% chance. We all know that it's gonna be either head or tail, but we just don't know which one. So that's a random experiment. So in that sense, outcomes are known to us. So you see that this is a plural, outcomes, not just outcome, because there are multiple outcomes possible, but we just cannot pinpoint which one unless we actually do it and see it. There's no way we can tell it in advance. Okay? So that's the definition of this random experiment thing. It can arise from some natural phenomena, like rain tomorrow. There are certain chances to it, but may never happen. So it's a random, but it's a natural thing. We have no control over such a thing. Just either rain or no rain. Just to wait and see. But we can make up one, like a coin tossing or rolling a die or something. Outcomes are known if you roll a die. Outcomes are any number 1 through 6, but we don't know it before we actually do it and see it. So in that sense, that's also a random experiment. But that's not natural. We just make it up and then just carry it out. So it can be artificial, but some other times it's just purely natural. And probability, which is the main agenda for this lecture note, is a certain way to model those outcomes. And what are those ways? It's just nothing but random number assigning. So there are a bunch of different outcomes on table, and you want to assign certain number to each one of those, which represent how likely those outcomes are gonna happen. So those numbers should be bounded by things like a 0 and 1. So if you add up all those assigned numbers, they necessarily add up to 1 or something. So certain rules that we need to abide by to make sure that those numbers function correctly, and those specific numbers, the way we assign those numbers to different potential outcomes, is called the probability. Further definitions: a set of all possible outcomes from certain random experiment is called the sample space. Very important terminology. Sample space includes every possible outcome. You shouldn't leave anyone out. Notation wise, it's either S or this. How do you read this? Speak it out. It's called omega. It's a Greek. A lot of things are Greek. It's omega. Uppercase. I forgot what the lowercase was, but there must be some corresponding lowercase. But we read it as omega. More common notation for the sample space, just a big S, because it's starting with S, sample space. Event is any subset of the sample space S. So since sample space supposed to include every possible outcome, you can come up with some subset of that. So those subsets are called events. And two possible kind, the occasions. The event is a subset might have only one outcome in it, one element in it. We call that sort of events as a simple events. Simple as it is, only one element or one outcome in it. If there's a more than one, two or three, or many more, that one is called a compound event. It's just a name, nothing more. We never will be asked what's the sample mean or not sample mean, simple event or compound event on the exam. Just for convenience, we just define this. Some examples to deliver the message clear. Random experiment could be a single die is rolled. You just get some fair and single die and then just roll it. Sample space, obviously all these number, integers 1 to 6. No other possible outcomes, that's it. Completely exhaustive. Nothing else is left. Simple event, any subset of this the defined sample space, collection of positive integers 1 to 6, only 6 are possible. Either the first, the simple event contain this 1, or just 2, or just 3, and all the way to the last possibility of just 6. Nothing else. Only 6 simple events are possible. Compound events are more possibilities. One of them could be like an event of getting an even integer. You know what even integers are. But then the restriction in this case, even integers among these 6. And these are obviously the second one, fourth one, and then the last one. Put these 3 elements together, and that constitutes, make up this compound event of getting an even integer out of these 6. So that's a subset of the sample space. Pretty simple. Second example, you can roll 2 dice instead of 1. So then you're dealing with the two dice instead of 1. So outcomes are 2 sets. So obviously the sample space is a collection of these all possible outcomes from each one of these dice roll. How many elements in the sample space? How many of them? Yeah, 36. 6 times 6. And simple events, 36 are possible because in total 36 elements belong to the sample space. Could be like a 3 and 4. This is just a one outcome because you did it twice. You don't separate them. So 3 and 4 make up for one outcome because you simultaneously roll 2 fair dice. So that's a valid example of the simple event because only one element inside. Or it could be 5 and 6, or it could be 6 and 6 and many more. 36 of them. Compound events, similar as before, can be easily defined. One example could be define an event such that you get the same outcome from both trials. So there will be 6 possibilities. You get 1 from both, 2 from both, 3 from both, and so on. There's 6 possibilities. But you have to include all these 6 outcomes in one set. So since the number of elements is more than 1, it's called a compound event. If the experiment is carried out simultaneously, not simultaneously, sequentially, so you first toss something and then observe the outcome, put it down, and then go back and try again. That's a sequential. But previously we did it simultaneously, so it's different. If you roll two dice, hold two dice in one hand and just toss them, everything is at the same time, simultaneous, but you can do it sequential. So sequential means you first try one thing, observe the outcome, put it down, and then repeat it. So there'll naturally be a time sequence. So the first trial, if it's a fair coin tossing, either heads or tail, no other possibilities. But then two subsequent similar distinct outcomes follow depending on whether you follow this top route or bottom route. If you go up to this top route, that's the case when you come up with hedge from the first toss, and then for the second toss, you equally, similarly, get either hedge or tail. So in the end, if you belong to the first case, the two potential outcomes are hedge, and second case hedge and tail. But in the beginning, you get the tail from the first toss. The similar, you have two different outcomes from the second trial, either hedge or tail. Then you end up with either tail hedge or tail and tail. So number of possibilities the same as before when you just toss them twice, not twice, at the same time. But in terms of the sequential movements, there's a quite substantial difference between this and the previous experiment that we just thought about. Things are simple and moving fast, but it doesn't mean that they are not going to be used. Further set-based relationships and notations and definitions, 5 of them, will be used when we get to Venn diagram. First one is a complement. So notation-wise, that's A to C. And A is any subset of the sample space. If you raise it to the power of C, that becomes A complement. And definition of this one, set of all simple points that are not in A. So the key word in here is this, not. You have to make sure that the element doesn't belong to A. As long as it doesn't belong to A, that's okay. You can put it in. So anything else, things that do not belong to A, you can put that into A complement. Define two events A and B, and they can be disjoint. Very important definition. Different name for the same thing is a mutual exclusiveness. So whenever you see the word disjoint, you automatically think of this second word, second expression, mutual exclusiveness. We call that as a disjoint sets. If this satisfied, there is no common simple event, nothing in common. So set A might have like 3 or 4 elements in it, but none of those elements are shared by the second set B. Then we say that there's nothing in common, and then validly those two sets are disjointed. Notation wise, we say that this thing, does anybody know how to read this? This cap thing? It's called the intersection. Or either some people call it cap because it looks like a baseball cap, but less common name. You read it as A intersection B. And what's this then? 0 slash. What do we mean by this thing? There's a 0 and then you slash it. Well, of course it's nothing, but you don't say nothing. There's a name for that. What do we call it? Empty set. Yeah, the name for this is empty set. We call that as empty set. Empty means there's nothing inside, so it's just empty, void, empty set. So if those two events, A and B, are disjoint, have nothing in common, the compact way to say that we say there's A intersection B. Common area of A and B is nothing, doesn't exist, so it's empty set. Similar but quite different notion of intersection can be defined. Intersection of A and B, we read that as either A intersection B or A, well, we defined it, cap B. Set of all simple events common to both of them. So the keyword in here is both. Pick up any event or any element. If it belongs to both A and B, it belongs to A and also it belongs to B, then this one necessarily belongs to this intersection of A and B, because that's the way we define this intersection. Set of all simple events common to both A and B. Similarly, we can define union. This one reads as A union B or A cup B, because it just looks like a cup. Less common way to call that, but some people still call that as a cup. So I call that as A union B. Set of all simple events, the key thing is it's either in A or either in B or maybe in both of them. All three occasions are okay and acceptable. Doesn't matter which one, or maybe two of them, or maybe all the three. That's okay, as long as it satisfies one of these criteria. And last but not least, we can define independence. If events A and B are independent, we mean that one event, occurrence of one, doesn't necessarily mean the occurrence of the other. There is no connection or relationship between the two. What are some of those examples of independent events? Example. Define two events that are independent to each other. So I'll give you one event. We have a rain tomorrow. What's completely independent of that? You have a headache? Well, there might be some connection. Some people are sensitive to those weather conditions. So if one event is a rain tomorrow, completely independent from that could be come up with something. They're complaining. What could be like I don't know. You have a wine? No, that might be related. You toss a coin and come up with a hedge or something. It's completely free of weather because you do it inside. Okay. But the important thing regarding these 5 different definitions, some people confuse the second and the fifth one, but they are different. So the events could be still disjoint, but not independent, and maybe the other way. They are independent, but not disjoint. There are plenty of those examples. Right? So there are plenty. And I might actually use some of these as homework questions, or maybe exams. But think about it. What events could be still disjoint, but not independent? Or the other way around. So there are 2 events that are independent, but not disjoint. So the one example we just said it, rain tomorrow, that's completely independent of getting a hedge from the random toss, coin toss, but there might be intersection between the two. Right? They're not mutually exclusive. It's possible to have both of them. You toss a coin and you have a hedge, and then you wait tomorrow and then you have a rain. That's possible. So I mean, that's possible. so they're not disjoint. If they're indeed disjoint, probability should be 0 of having both of them, but that's obviously not the case. Or the other way around, 2 events are disjoint, but they are dependent. What could be the example? So if you define event A, B, toss a coin and get hedge, and event B is a rain tomorrow, they are independent, but they are not disjoint. It is possible that you toss a coin now and then get hedge, then wait until tomorrow and you actually see rain. That can happen. So probability is non-zero. So they are not disjoint. But what are 2 potential examples, events that still disjoint, but not independent? Compilman usually do it. Like define A as like rain today, define B as no rain today. They are disjoint obviously, but they are not independent. They are dependent actually, because A means not B, B means not A. So the probabilities are each affected, right? So usually the negation, complement of certain set is a perfect example for disjoint but not independent because they are dependent. Or coin tossing. Event A could be you toss a fair coin now and get hedge. Second event is you get tails. They are disjoint. It's just the same toss. You cannot have both of them. So you cannot possibly have both of those outcomes at the same time. So they are obviously disjoint, but they are dependent. Whether you get heads affect whether you get tails. So there's no way you can separate them, although they are still disjoint. So the key point is that this second notion, whether the sets are disjoint or not, has nothing to do whether they're independent or not. A lot of people confuse them, but they're actually two separate, distinct ideas. You can come up with numerous examples in such the first criteria is satisfied, but not the second, or maybe the other way. But then I'll give you this example, which is more interesting. Say A and B are independent. A and B are two events. Independent. The light on. Still saying B, introduce the third one C. It's independent. But then the question is, are A and C independent? What do you think? So three different events, A and B, we do know that they are independent. B and C, we do know that they are also independent, but does that necessarily mean that A and C are also independent? If it's no, provide example. It's called a counter example. If it's yes, usually go ahead and mathematically prove it. But if it's not, then you provide example. So what could be the example? Huh? C is A? No examples like the rain or coin tossing or chances of you have a burger at McDonald's or something like that. Provide specific events, A, B, and C. There are like numerous examples. Like A could be like you toss a coin now and get heads, and B could be like you go to McDonald's. There's no relationship, independent. But B is you go to McDonald's for lunch, and C could be the coin tossing give you taste. Still independent, but A and B are dependent. A and C are dependent. So whenever this notion of independence is included, you can easily think of some composite like the complements, negation of one thing like a coin tossing, heads and tail. Come up with a third event which is independent to both of them, but these two still not independent. Many of these examples are possible. So I'm trying to say that the being disjoint is one thing and being independent is different. Now, the fun stuff, Venn diagram. Nothing but a picture that you get to define the entire sample space and relevant events inside. So just this picture. I feel like we go back to elementary school or something. So there's one big rectangle outside, that's the sample space. The whole collection of possible outcomes, events, when you carry out certain random experiment must be included inside. Otherwise, you cannot even define as far as that specific event is concerned. Any subsets or events are denoted by those smaller circles inside. So if you imagine two different events, toss a coin or either heads or tail, that's event A, getting heads, and the other event getting tails. So denoted by those smaller circles. How come the sample space is rectangle and then events are circles? I don't know. Somebody started doing it and we just follow suit. If you want to do it in your way, you can just do the circle for S and rectangle for A and B, but still the same idea. But conventional notation is that this big box thing, rectangle for the sample space and smaller circles inside for those individual events. The one nice thing about this Venn diagram, we can easily depict those ideas of being disjoint, independent, not quite independent, the union and complements and intersections all together, not all together, separately, but a very easy way. So to represent those intersection of A and B, you just simply show this intersection, the common area that belongs to both A and B, which is nothing but this tiny part, and you shade it, and that's going to represent the intersection of A and B. Similarly, you can define the union of A and B, and then you have to shade the entire two circles. That one belong to A, and also that belong to B. Maybe the part that belongs to both A and B. Necessarily, all these three parts must be included by those union. Complement, negation of it, first a circle, and then denote that as A, and then complement of A still belongs to the sample space, but doesn't belong to A, which is the rest of them. If it's a mutually exclusive, which means that the sets are disjoint, no common area, you just separate them completely. No overlapping of each other. So A and B, that represents those two mutually exclusive or disjoint events, A and B. Famous laws, the Morgan's laws, when it comes down to intersection and unions, states two different cases. First, consider the union of A and B, and if you take the complement of the union, that's equivalent to having the intersection of A complement and B complement. Similarly, you take the complement of the intersection, A intersection B, you consider the complement of the whole intersection, that's equivalent to having union of A complement and the complement of the second set, which is B. The Morgan's law. I think he's a French or something. He must have came up with these ideas. I guess I never checked it. Otherwise, people would name it after him. Very handy properties regarding those intersections and unions. Do some examples. Using the Venn diagram, we can depict whatever the event that might correspond to specific things that we have in mind. One example is this one. Say that there's an engineering firm, and the company is about to construct 3 different power plants at 3 different locations. So since there are 3 different locations or sites, we can define 3 different events. A1, defined as events such that the plant at the first location is finished. Construction is done by the construction date, and that's the first event. Second event, similarly, you can define that as event that the plan in the location 2, second location is also completed by the contract date. And then similarly, you can define the last event, such that the plant is supposed to build in the last location, location number 3. So also completed by that specific contract date. So define these 3 specific individual events, A1, A2, and A3. And using Venn diagram, you want to describe what's the corresponding regions, depending on what events we deal with. First event that we deal with is this one. At least one of those 3 plants is completed by the contract date. And if you want to depict the area inside this Venn diagram that correspond to this specific event, that's going to be nothing but this. So all those elements inside this A1, A2, and A3 must be included because it's a union of all these 3. Is that this word at least? Whenever you see that the word at least, you think of those unions. Because it's okay either to belong to one or the other, or maybe both of them. Any one of these 3 occasions satisfy this at least thing. You pass the minimum bar. That's what it is. Second one, all the plants are completed by the contract date. How do you describe this one using Venn diagram? So let's do it together. I feel like I'm going back to elementary school or something. But it's just a 5-minute thing. You never get to ask again. So it's just routine thing that instructor is supposed to cover. It comes at the introductory probability class. So sample space is out there as a big box. You deal with the three sets, three events inside. Down here. So what's the area in this Venn diagram that corresponds to the second event? Here, right? Common to all those three, because that's the intersection. All the plans must be completed by the contract date. So first write that as a A1 intersection, A2 intersection, and A3, and then draw that picture, and that will complete the answer. Now, the third one states that this is the event that the only one plan at site 1 is completed by the contract date. How do you represent that using sets? A1, A2, and A3. How do you represent this event using those sets? So A1 should be there, and intersection complement A2, and exactly. What's that in terms of this picture? Well, simple. You just include A1 but not the other two. Now, the fourth one, exactly what plant is completed by the contractor? Started with the set-based one. How would you describe that? Only one plant. So starting with A1, so one possibility is this. And then, that's a one case. Now what? Union. A1, A2, A3, and then the last piece. It's quite messy. But what about in terms of picture? That's simple because the last one. Either the plant at first location is completed by the contract date, or both of the other plants are completed by the contract date. How would you describe this one using sets? So A1 should be there, and union, so either A1 or the both of the other two. So how would you say? In terms of this picture, do you describe it? Just entire A and the intersection between second and third A. So it should be this. More advanced definitions when it comes down to probability. First definition, probability, what is a probability? It's nothing but mathematical functions, and function that relates or assigns to each specific event inside the sample space some number, and the numbers must obey these following axioms. So it's just a number, and number gets assigned to all those possible outcomes, events inside the sample space. But this, the matching or mapping should abide by certain rules, and those rules are called axioms. So axioms in mathematics is very some important relationship or properties, but you don't have to prove it because it's so basic. So the first axiom that all those probability must abide by is this one. For any event inside the sample space, the number that's assigned must be either equal to or bigger than 0, but necessarily either equal to or less than 1 because it's a probability. Cannot go beyond 1, cannot be lower than 0 because negative probability is not allowed. Second important property, if you compute or figure out the probability corresponding to the entire sample space, that's always 1. It's 100% certainty, will always happen. Probability 1 means 100% chances. More involving one, imagine that they're like either finite or infinite number of the disjoint or mutually exclusive events, and probability of union over those is nothing but the sum of individual probability of those events. So if you have a hard time imagining what that is, only think about two events, event A and event B. So if A and B are disjoint, what that last axiom is saying, if you compute the probability of A union B, it's nothing but the sum of each probability. And you can generalize it to many others or maybe infinite number of sets or events. The relationship still holds. So given these three important axioms in probability, we now move on to deal with those less important but it's harder to prove propositions. Proposition 1 states this. Given the three facts, all the probabilities must be bounded by 0 and 1, and the probability of the sample space is always 1. And then if you consider the probability of union of either finite or infinite number of disjoint sets, that must be equal to sum of those individual probabilities. Given all that, now you want to prove that probability of an empty set, a set with no elements in it, is nothing but 0. And first step to follow in order to show this property is this one. For any event A, we know this. How do we know that? So any set A, first consider the probability of that, and then consider the probability of that complement of A, and if you sum up those probabilities, that must necessarily add up to 1. Why? Because of what axiom? Axiom number 3. Axiom number 3 states for any disjoint event, equivalent to A union A complement, right? So that was the third axiom, and then you just apply it. Because A and A complements are disjoint. So treat this A complement as B, then this relationship follows. But then what is this? Sample space. Yeah, that's sample space. But then because of the second axiom, that's 1. So that's the result that we have here. Now move the second probability to the right hand side, and you have this. From this, so from this to this is obvious. You just move one term to the other end. And then from here, we know that the probability of empty set is 0 because y. So from here, how do we lead to this one? How do you know that given this is true? So that's the eventual thing that we want to prove. Probability of any empty set is nothing. You can prove it if you replace A by empty set. Because this relation must hold for any possible set. Empty set is one of those possibilities. So if you replace A by empty set, what you're having P empty set 1 minus P empty set complement. But what's the complement of the empty set? Sample space. So that's equivalent to saying this. But then by the second axiom, this is 1. So you do know that that's 0. For any events, now they don't have to be disjoint. Union of A and B can be computed by first the sum of these two individual events, P of A and P of B. But then you shouldn't forget to subtract the probability of the intersection of A and B. In the case of the third axiom, we just didn't deal with the last term because that's 0. But if it's just a usual case where the common area is allowed, you actually have to take this one into account. And you can generalize it to the case of 3 different events, A, B, and C, although we are not going to deal with this case in this class. But the second one, the middle one, is kind of important because we're going to use it next example here. So last one for today, define 2 events, rain on Saturday and on Friday. It's about 40% chance of happening. Second event is defined that event for Saturday, which is about 80%. Double chances doubled. And then further went on, then we given the information that the probability of having rain on both Friday and Saturday is not so small, 30%. Then the question is, what's the probability of rain on either Friday or Saturday? It's nothing but the application of the second proposition. Just copy this one down here, and then we given the probability for each. 40%, 80%, then subtract the 30%, and then we easily figure out the answer should be 90%. That's it for the probability. And any other question you can ask now or after class. Otherwise, see you all next week. Solutions will be posted by tomorrow night, I think, Wednesday. And if you didn't get it by Wednesday, you can remind me by sending me email, but I'll do it.